Hi, this is Qiong from C++ Virginia Tech. Here I'm going to introduce our work on the design and the implementation of a three-phase, high-efficient active front end for more electric airplanes. Our work aims at building a 3 kW three-phase active front end with high efficiency without active cooling. This converter may also work at high ambient temperature. Here we want to utilize the advantages of interleaved systems. They are better power quality due to the canceling effect, lower loss because intrinsically interleaved systems are parallel systems, and due to the spread loss, it may achieve better thermal management. This graph shows the basic configuration of an interleaved system, where we have two subconverters gated with interleaved gate signals generated by interleaved carriers. By doing so, we can fully utilize the benefits of interleaved systems. This graph shows the topology we have built. It is a two-channel interleaved Vienna rectifier. From left to right, there are input sources, boost inductors, couple inductors for circulating current attenuation, phase lags that shape the input current, DC bus capacitors, and load. In Vienna rectifier, by using Schottky diode, the reverse current loss from switches can be eliminated, which reduces the switching loss. It should be noted that the design of couple inductor is critical in this converter because Vienna rectifier is a current commutated converter, which means that the output voltage of each phase lag is not only determined by the switching state, but also determined by the polarity of the current. Here, the couple inductor should be large enough to ensure the functionality of the converter. To achieve the optimized design, we have gone through this design procedure. Starting with the topology, converter specification, and standard, we selected the modulation scheme for this converter. Here, we have selected discontinuous PWM in order to reduce switching loss. Then, by going through this sweeping program, where all the design variables are swept, we can find the optimized design that achieves highest efficiency. The relationship between switching frequency, total loss are listed here. For this work, we have picked up the design at 22.4 kHz for each subconverter. The total estimated loss is 26.5 watt at 3 kW output power. Here's the converter prototype. The source, boost inductors, couple inductors used for circulating current attenuation, 6 phase lags, and the DC bus capacitors, and those are the terminals for outputs. These two neighboring phase lags are interleaved with each other, and these two are interleaved with each other, and these two are interleaved. For the following demonstration, we will measure the waveform of the two output voltages of these two interleaved phase lags and the current flowing through them. Here are the experimental waveforms of the converter prototype at nominal load, from top to bottom. These are the two output voltages of the two interleaved phase lags, the voltage difference between the two phase lags, the two currents, and the circulating current. When we zoom in, we can clearly see the difference between the two voltages as shown here in orange waveform. The two currents are very similar to each other due to the existence of the couple inductor, and you can see here the circulating current is very close to zero. This slide shows the loss breakdown, loss and the temperature measurement result. The measured total loss is 27.7 watt at nominal load, achieving 99.08% efficiency, which matched with the prediction. The measured device temperature at lab ambient without fan cooling are listed here. The highest temperature occurs on the diodes, where there is high conduction loss. Still, the temperature is low enough to ensure functionality. That's all about our work. Thanks for watching. See you next year.